In this next group of exercises, we're going to look at when a simulation is correct or incorrect. So we have here, explain what's wrong with each of the following simulation designs. And for exercise 15 and 16, we're going to look at that. It says a roulette wheel has 38 colored slots, 18 red, 18 black, and 2 green. To simulate one spin of the wheel, let numbers 00 to 18 represent red, 19 to 37 black, and 38 to 40 represent green. Well, we need 18 numbers to represent a red, 18 numbers to represent a black, and 2 numbers to represent green. Here, though, from 00 to 18 is 19 numbers, and 38 to 40, 38, 39, 40 is actually 3 numbers. So we have 2 extra numbers. So what's wrong is that the numbers are not assigned correctly to represent the probabilities correctly here. Part B says about 10% of U.S. adults are left-handed. To simulate randomly selecting one adult at a time until you find a left-hander, use 2 digits. Let 00 to 09 represent being left-handed, and 10 to 99 represent being right-handed. Move across a row in Table D 2 digits at a time, skipping any numbers that have already appeared until you find a number between 00 and 09. Record the number of people selected. That is actually a very good description of how you work with a random digit table. So that's a good example of how to describe it. The problem with this is a subtle one. 00 to 09 are 10 numbers, and 10 to 99 are 90 numbers. So the numbers are assigned correctly to appropriately represent the 10% of people who are left-handed and the 90% of people who are right-handed. The only thing that's wrong is it says go across the table 2 digits at a time, skipping any numbers that have already appeared. You don't have to skip numbers because each number you draw represents a percentage. So you're saying, I'm getting somebody who's a left-hander, I'm getting somebody in the group that's a right-hander. But each number doesn't represent an individual person, it just represents being part of a group of left-handers or a group of right-handers. So I don't need to skip repeated numbers. It's okay to use repeated numbers in this situation. 16A, if you read it, is exactly like 15B. The numbers are assigned correctly, but they ask you to go 2 digits at a time until you find 8 distinct numbers, no repeats. That's another way of saying we can't use numbers twice. But in this case, you could still use numbers twice. We'll see an example later on where you cannot use numbers twice, and I'll explain the difference between those. Number 16B says, assume that the probability of a newborn being a boy is 0.5. To simulate choosing a random sample of 9 babies who were born at a local hospital today and observing their gender, use 1 digit. Use randomInch 09 on your calculator to determine how many babies in the sample are male. Now, this is not a correct assignment of numbers because we should have an equal amount of numbers representing male and female. Since there's a 50-50 chance of male and female, what would make sense is to let 0 represent having the newborn being a male, and 1 represent female, and then generate 9 numbers. So you would write randomInt 0, 1, 9 to do that. 17, 18 give you two different scenarios each and ask whether it is a valid simulation design. So 17 says, according to a recent poll, 75% of all Americans regularly recycle. To simulate choosing a random sample of 100 U.S. adults and seeing how many of them recycle, roll a 4-sided die 100 times. A result of 1, 2, 3, or 3 means the person recycles. A 4 means that the person doesn't recycle. So what you want to do in evaluating that is to say, do the numbers assigned accurately represent 75% in one group and 25% in another group? Well, yes, they do, because we have 4 numbers. They're equally likely to occur. 3 of the numbers are representing recycling. That's the 75% group. And 1 number represents not recycling. That's the 25% group. So that is a correct use of a chance device. B, an archer hits the center of a target with 60% of her shots. To simulate having her shoot 10 times, use a coin. Flip the coin once for each of the 10 shots. If it lands heads, then she hits the center of the target. If the coin lands tails, she doesn't. Well, flipping the coin 10 times for the 10 random events is not a bad idea, but that will only give you a 50% chance of hitting the target, not a 60% chance. So that is not the correct assignment of probabilities. You would need to have something that could give you a 60-40 rather than a 50-50 chance. 18A. According to a recent survey, 50% of people, hey, I think I'll just say, hey, stop here and read 18A and B yourself and see if you can figure out what the correct answer is, and then turn me back on. But I'll start talking now if you don't turn me off. According to a recent survey, 50% of people aged 13 and older in the United States are addicted to texting. To simulate choosing a random sample of 20 people in this population and seeing how many of them are addicted to texting, use a deck of cards. Shuffle the deck well and then draw one card at a time. A red card means that a person is addicted to texting. A black card means that he isn't. Continue till you have drawn 20 cards without replacement for the sample. Well, the 50-50 probability is assigned correctly since we have 50% red cards and 50% black cards in a deck. What doesn't work in this case is the without replacement, because if we don't replace the decks in a deck of cards, as we continue to draw cards out of the deck, the probability of getting a red or a black changes every time. If I draw a red card, then the next card I draw will have a higher chance of being a black. If I draw 3 or 4 black cards in a row, then the next card I would have a higher chance of being a red. So the probability doesn't stay 50-50 every time. So that's what's wrong with that one. Part B is actually correct. We say they're correctly using 00 to 94 or 95 of the numbers to represent the serves that he hits and the other 5 numbers representing the serve is out.